welcome back. So today's lecture is going to be all about calculating, how do you calculate the, I say moments of Z, mainly just the expected number of solutions of your random constraint satisfaction problem. And I'm going to start off with some of the pitfalls that can happen if we're doing this in, say, the Erdős-Renyi random setting. But when the underlying graph is Erdős-Renyi, it's usually easier to calculate the expected value. It's just that some of the time the expected value might be a lot bigger than the typical value. And we'll see how that can happen. On the other hand, for the random regular graphs, it's a bit harder to write down like the expected number of solutions because of the dependence of the edges. But more often the expected partition function will be a good, will tell us what the, will be of the same order as the partition function itself. Okay, so we'll start off with a simple example. Erdős-Renyi random graph and K colorings. And it was pointed out that I showed myself as a sort of not really a real American by including U in colorings, but okay. So we want to calculate expected value of Z, the number of colorings, and well, there's k to the n total number of ways I could assign colors to each of the vertices. But let me say that I'm going to have pi times n number of vertices of color I. And so I'll sum over the possible choices of pi, and then how many ways are there of assigning, the n vertices so that exactly pin of them are I? Well, it's just a multinomial formula. Pin factorial. And then I want to multiply this by the probability that a given assignment of vertices is actually a coloring. So it means that between each pair of vertices of the same color, I can't have an edge. And the number of pairs of those for each I is np I choose 2. Okay, and now we're summing over the pi here, but there's you can ask, which choice of pi would maximize this? And well, if you want to assign colors, what's the frequency of the PIs that will give us the most possible ways of doing the colors? It's just all of the pi being 1 over k. If you just assigned each sign colorings uniformly, you'd get a coloring that was basically balanced between all of the colors. So this is maximized with all of the pi equal 1 over k. And here, this is also maximized. We want to sort of minimize the sum of the n choose pi. So I could write this as a sum over I of n choose pi, or npi choose 2. And this is basically like 1/2 n squared pi squared. And if I want to minimize the sum of pi squared, I should also choose them all to be 1 over k. So if I wanted to just calculate the sort of exponential growth rate of this, I'm going to add in a plus little o of n term here to sort of ignore, sort of lower order terms. also, the number of these pi, I mean, I need pin to be an integer, so there's only n choices for each pi, and so at most like n to the k number of terms in this sum, so that I can also sort of wrap up in this little o of n term, and just concentrate on the term that's the biggest value there. And this first one, well, these are factorials. I could just sort of substitute in Stirling's formula. If you go through that, you'll get e to the n times log of k. Basically, that you get the number of possible colorings is k to the n. And then if I approximate 1 minus d over n as about e to the minus d over n, then I'd get minus d over 2 n times 1 over k. So this sum would be like k times n squared 1 over k squared over 2. Okay, so this is at least up to the exponential growth rate, the expected number of colorings. Okay, so we could ask, is this a good approximation to the number of colorings? Well, let me do the same calculation, or almost the same calculation, but just change the graph very slightly. So let's say instead of having gn d over n, I just condition on there being exactly dn over 2 edges. So I'll call this m. And so this sometimes you write as the model gnm. It's random graph with n vertices and m edges chosen uniformly at random. Okay, and I'll write z prime for the number of colorings of this graph. So it's the same model except with conditioned on the number of edges. So how does that affect the expected value? Well, I could sort of go through the same calculation. Except now when I'm calculating the probability that it's a coloring, I want to say, well, okay, for each of these m edges, what's the probability that it connects two vertices of the same color? And well, that should be, let me just, I mean, this is a very easy calculation, but it's also very easy for me to just write the wrong thing. So PIN, okay, choose 2. So this is the number of pairs of vertices that have the same color over, and choose 2. Okay, I think actually I could have worked that out myself, but okay, and that to the power of m. And now we could do the same thing, right? This, so again, this will be maximized by all the pi being equal to 1 over k. So, and we get the same n log k from the multinomial for, right? And here, well, this will work out as 1 minus 1 over k, and m is, and choose 2, so we'll get dn over 2 is log of 1 minus 1 over k. So in terms of the exponential growth rate, in the formulas, we've got minus 1 over k here, and log 1 minus 1 over k here. And, well, just by the concavity of log, minus 1 over k will be bigger than log of 1 in this case. So this expected value is exponentially bigger than this one. So expected value Zn is sort of much, much bigger than Z prime. So so this one sort of can't really be a good approximation to the typical number of solutions. Okay. Whereas it turns out that that conditioning on the number of edges first will, at least up to a certain point, give you the right approximation. So why do we get two very different answers in doing this? So imagine, so it's because in this case, you know, the only difference is there's some fluctuation in the number of edges. The number of edges in this graph is about a Poisson with mean dn over 2. I mean, it's a binomial. So there's some chance that it's much bigger or much smaller than its expected value. So if I write the probability that the number of edges is, let's say, less than d minus epsilon on 2 times n. So d over 2 times n would be the expected value. Well, this is now a large I mean, the number of edges is just a sum of IID random variables. So this is just a sort of standard kind of large deviation question. How big is this? And so Cramer's theorem will tell you that there's some sort of exponential growth rate. And when epsilon is small, it will be about, well, let me just write it as a lower bound, but e to the minus a constant times epsilon squared times n. So having this small number of edges is a rare event. But the point will be that in the exponent, you have both. I mean, yeah. So with a, I mean, I could, with a maybe slightly different C, it would be true the other way around too. I mean, okay. Really, I should say it's equal to some f of epsilon times minus f of epsilon times n, and f of epsilon is sort of to first order like c times epsilon squared, maybe some other c. So I have an upper bound, but I also have a lower bound of this one. So the point is that these graphs, which have sort of fewer edges than normal, and basically fewer constraints than normal, are rare. But if epsilon is small, they're not that rare. Okay, and okay. So what if I wanted the expected value of z, indicated that the number of edges was less than or equal to d minus epsilon on 2 times n. And actually, maybe I'll say exactly equal to. So this would also be true if I replaced less than or equal to here with equal. Okay. So, well, this is just, it's the probability that the number of edges is equal to d minus epsilon 2n times the expected value of z given the number of edges times n. And this is exactly the calculation that I just did here. Okay, so we'll get e to the minus something that's at least e to the minus epsilon squared times n. And then I could write in this formula, but I want to let me write it like this. Expected value of z prime. So this is where I'm conditioning on the right number of edges, times 1 minus 1 over k to the, I guess, minus epsilon on 2n. Okay. And or, yeah. E to the, and so this, well, so this is something that's like, one constant times epsilon minus another constant times epsilon squared times n. So when epsilon is small, this will be exponentially large. So the contribution to this expected value coming from these very rare graphs that have fewer edges than normal is sort of exponentially bigger than sort of this conditioned expectation. So what that says is that it doesn't make sense doing this unconditioned expectation because very rare graphs are going to sort of dominate the expected value. I mean, it makes sense as a formula you can write, but it doesn't give you sort of insight into what the typical value of z will be. Okay. On the other hand, so here we see sort of like how the fluctuations in the graph and the number of edges sort of really affects this expected value computation. But it turns out that this is sort of really the only obstacle in this case. And so if so let me just say, so but actually, if we look at expected value of z prime, when d is bigger than 2 k log k, then this will tend to 0. So this is sort of gives us an upper bound. So just plugging d in there. So this will give us sort of an upper bound on the number of when we can have colorings. So if the degree is bigger than 2 k log k, you won't see any coloring. So this at least gives you an upper bound on when you expect to see colorings of the graph. But what about a lower bound? Well, for that, we'll use the second moment method. And what this will say that, well, okay, if expected value of Zn squared, expected value of Zn squared goes to 1, then by Chebyshev's inequality, this implies that Z over expected value of Z will converge to 1 in probability. Okay. But in a lot of cases, for the problems we'll be interested in, this doesn't happen. What will happen instead is, and this is including in the colorings case. So if we condition on the number of edges and take the second moment over the first moment squared and this will converge to some positive constant. And then if the second moment method will say that, well, the probability that z is bigger than, say, 1/2 times its expected value is greater than 0, or so, like the inf over n of this. So it will say that at least with some probability, the number of colorings is at least positive. So if you can show this, that the ratio of the second moment over the first moment squared converging to a constant, then you'll show that there are, you at least have a positive probability of having, that doesn't tend to 0 with n, of having some colorings. And then you would have to do some sort of extra work to show that actually this probability is tending, or that the probability z greater than 0 is tending to 1. And I'll talk a bit later about how one can do that, but let me just tell you the theorem in this case. Okay, I think this was the lower bound on where I can write. So this is a theorem of Akliopoulos and Nowell from 2005. And they showed basically that if d is less than 2k log k minus a constant, so not exactly this upper bound, but just a small amount less, then indeed we have Zn prime squared converges to a constant. And they also showed that it's greater than 0 tends to 1. So they could indeed do this second moment calculation.
Can you clarify where there should be primes on any of these? So here you have how about up there? Like you have a conditional prime?
Yeah, everything should be prime. Everything should. Yeah, sorry about that. And so actually,
You care about z, right? Not z prime.
Yes, yeah, that's right. Yeah, and so of course, yeah. But if we can show that z is positive, then for like a slightly bigger value of d, then we'll also then show that if z prime is positive for a slightly bigger value of d, then that will also imply with high probability that z is as well, because you can couple the two. And of course, the more edges you add, the fewer colorings you have. There's a sort of obvious monotonicity in that. Yeah.
Just to clarify, what was the definition of z prime?
Z prime was we condition on the number of edges. Yeah. And actually, from here on in, I'm going to, not have primes anymore. Z will always do this conditional look at the model G and M. So even if I say G and D over of N, I will mean this one. that will be the notation from now on. And yeah, it's precisely because we'll mostly be working with moments from now on, and they're just they can sort of almost never work out properly when you're not conditioning on the number of edges. Okay. So how would you do this second moment calculation? Well, doing the second moment is calculating the numbers of pairs of colorings. So you'd want to sort of for each vertex, assign a pair of colors and check the probability that both of those are colorings. So you'd want sort of have Pij as the n to be the number of vertices that are I for their first color and j for their second. And then do a sort of similar optimization process over that, but then it becomes a much more complicated calculation to do. But we're sort of, yeah, okay. So I won't go through the details of that calculation. One thing I wanted to talk about is why you get a convergence to a constant here and not to 1. Because this, it would be much more convenient if the limit was just 1 here. So what goes wrong with that? Well, we could imagine sort of forming our graph by starting off with G0, the empty graph, and then sort of adding edges one at a time. So to go from GI to GI plus 1, you just add in one random edge. And now add one edge. Okay. And so what can we say about this ratio? So let's do things in the really simple case of d less than 1. So the average degree is less than 1. And we said that what do these graphs look like? Well, there's no giant component. All of the graph looks like basically just a collection of trees, lots of isolated vertices, and maybe the occasional small cycle as well, or a tree plus one extra edge. Okay. So, and the biggest of these components is of size log n. So what happens when I add in one extra edge connecting, let's say, vertex u to vertex v? Well, this ratio will just be the probability under the graph GI that sigma u is not equal to sigma v. So the number of the colorings that we're losing are exactly the ones where u had the same color as v before we added in this edge. Okay, but in the picture I drew, these were in different components. This tree was not connected, was a different tree to this one. So just by symmetry of colorings, each vertex is equally likely to be any of the k colors. And if you're in different components, they'll be independent of each other. So this probability will just be 1 minus 1 over k, as long as you pick them in different components. And almost all of the time, that's what you're going to do. These components are very small. If you pick two vertices to connect between, you're very unlikely to pick two that are in the same component. But occasionally, you might have, say this component, and then you decide to add this edge in and form a cycle of length 3. These ones were not independent. So if this one is, let's say, blue, then the probability of this one being blue is 0. And then the probability of this one being blue would be 1 over k minus 1. So the probability that, so this was u and this was v, sigma u not equal to sigma v, in this case would be 1 minus 1 over k minus 1, which is not the same as this. So the only time when this ratio changes by something that isn't 1 minus 1 over k is exactly when we're creating a cycle. Okay. But within a tree, it's sort of easy to calculate, if I have two vertices at distance L from each other, what's the probability that they're the same? Because if I look at the colors along some ray in the tree, that's just doing a Markov chain, where the transition probability is you choose a random color that's different from the previous one. Okay. And so if you go through this calculation, ZGM, so if there were no cycles, it should be just 1 minus 1 over k to the m. But then I need a correction factor. J equals 3 to, well, we'll have to think about what we should put in as the end of the limit, but the correction, maybe I won't go through the calculation of it, but it's minus 1 over k minus 1 to the j. Minus 1 over k minus 1 is the second eigenvalue of the Markov chain if you look at colorings along a ray in a finite tree. So that gives you sort of, and then this is to the power of the number of cycles of length j. Okay, and so this is the right correction factor that you need. So if I look at expected value of, and let me just call this alpha j, GM, so if I want to remove these fluctuations, I should sort of divide through by this term to make this constant. Squared. This does converge to 1. So this will be concentrated. And so this calculation sort of is not hard to show in the case of d less than 1, but actually it will, even though we made this sort of correction term for it formally only made sense when d was less than 1, and our graph just looked like a collection of disjoint trees. When d is bigger than 1, we'll have a giant component, and lots of the edges we add in will connect pairs of vertices in the giant component. But this will still hold even up to this point. So it tells you that once you correct for the number of cycles you see, then the partition function really becomes concentrated. I should have maybe said what here, in terms of how large a factor of, j equals 3 to what, I would I can really take anything here that's diverging. So something like log n would be fine. Yeah.
So you don't use your incremental construction here to get the formula below, right? You just, I don't really see. You cannot get this by induction, for instance.
This?
Yeah.
No, this I mean, yeah, you. So
You were only explaining
the moment calculation you can't. Oh, okay. So when d is less than 1, then this formula is exact, and you can really just prove it by induction, because sort of if you look at the change you get from adding an edge, either you connect vertices in 2 different components and it's just a 1 minus 1 over k, or you connect 2 vertices in the same component, you form a new cycle, and then you sort of increment one of these counts of cycles, and then it's still exact. The point where it would break is that if you started having components with more than 2 cycles, but with probability tending to 1, you don't have that when d is less than 1. Okay.
The probability of choosing a vertex that is in the same component you are isn't killed by something log n over n.
Oh, okay, yeah. So you can have cycles that are bigger than log n. So this is just sort of a better and better approximation as this upper bound tends to infinity, so that the effect of the biggest effect you'll have is 3 cycles and then 4 cycles. The million cycles will have only a sort of very small effect on the total number of colorings, and so right, this actually with log n here, this wouldn't be an exact formula, because we would have cycles of length order log n, but it would be right up to a sort of 1 plus little o of 1 factor. Oh no, sorry. When d is less than 1, actually, the biggest cycle will be of size order 1. So I take it back. This really will be true with probability tending to 1. Yeah.
So is that an m or n, like z?
This
or this is m.
This is m, and this is like.
But why isn't that n plus 1 then? If you have m edges,
Have
cycles bigger than m plus 1.
and oh, and also one obvious thing I forgot as well was that I should start with z0. So this is like k to the n. And so each time I add in an edge, it should decrease by a factor of 1 minus 1 over k. So if I add m edges, I should have this. So I'm not.
No, the upper bound, why isn't it m plus 1? Like your upper bound on
Oh.
the product.
Oh,
If you have m edges, you cannot form.
Oh,
It's just like you want something independent of m in your upper bound. Is that what you're?
yes. So I want. Okay. When d, so I sort of motivated this with the d less than 1 case, and in that case, the biggest, like the expected number of cycles of length k was like d to the k. So it's tending to 0, or d to the k on 2k, so it's tending to 0 with k. So in that case, I'm not going to get any large cycles at all. So I mean, this formula won't be correct with probability 1 because there is some probability of having, a component with several cycles in it, and then this formula would not be right. But when d is less than 1, with probability tending to 1, you have none of these, and also with probability tending to 1, you have no large cycles either. So putting anything here that tends to infinity should give me the right formula for that. But I wanted something smaller than log n so that we're not counting really large cycles if we, in the case where d is bigger than 1, because then there'll be a lot of those. Yeah, I think.
But the Z is a partition function, right?
Yes.
So what does it mean for the partition function to be that with that probability? I mean, you are summing on all over overall the configuration. So what does it mean for probability?
I mean, so I guess I mean that the probability that ZGM equals this formula tends to 1. So I mean.
I'm still not understanding because the partition function you are summing over all your possible configuration. So
Yep.
you are raising the probability, right?
No. I mean, the graph is random.
So you keep the,
Yeah.
okay.
Yeah.
You are not, okay.
I'm not taking the expected number. I'm just,
Sorry.
yeah. So that's what, yeah. So the randomness is in the graph.
Okay.
Good. Any other questions? Okay, so to do the second moment method, you should account for the number of cycles if you want to get a limit of 1 here. And that's becomes and there's sort of a theory for how to do that. But I don't think we won't have time to go through the details of that. But it boils down to sort of essentially saying, well, what would be the effect if I added in 1 extra cycle? How would that change the partition function, or j extra cycles? And then there's a sort of recipe for how to recover this limit. Okay. So I wanted to do another sort of pitfall of where computing expected values on Erdős-Renyi random graphs can go wrong. And so now let's look at independent sets. So I'll let Z will be the number of independent sets. Okay. And again, so this will be on G and M. So we'll have sort of some giant component and then some other smaller components, some isolated vertices, and I want to calculate the expected number of independent sets. And so I can break up the components of the graph in the sort of natural way of those of size 4 and those of not size 4. So we have components of size 4, which either look like this or look like this, and everything else. And I can write the total number of independent sets as the number of independent sets on the components of size 4, and the number of independent sets on things that are of not size 4. Okay, and I'm just going to condition on this and show that just the fluctuations from this part are already really problematic. So we have these 2 types of size 4 components, and you can count how many independent sets there are of them. So in this one, there's 1 of size 0, 4 of size 1, 3 of size 2. This one has 1 of size 0, 4 of size 1, 3 of size 2, and 1 of size 3. So there's 9. So this type has more than this type. So I'll let S be the number of components of size 4, and R be the number of these paths of length 4. And now I'll also condition on S and everything, the number in the rest of the graph. So given that I tell you that there's S components of size 4, we're sort of, first of all, I mean, S will be linear in N. P here will be basically 1/4 times the probability that the Galton-Watson branching process will have size exactly 4. So you can compute what this P should be. And it will be concentrated around this. Okay, so if I tell you what, and given S and also everything in the other components, R is just a binomial, S, and then it turns out that these so you would sort of group vertices, group all the 4S vertices into S groups of 4, and then you've got to choose whether they're connected up like this one, like the type 1, or the type 2. And it turns out that there's 3 times as many ways to connect them up in type 1 as type 2. So you get a binomial 3/4 of the number of them. So once I've conditioned on everything else, there's still some randomness in what fraction of these two that we have. So the typical value of Z4 should be like 8 to the 8 to the R times 9 to the S minus R. And typically this should be like 8 to the 3/4 times 9 to the 1/4 to the power of S. Okay. But if I wanted the expected value of Z4 given, let's say, S and everything else, then we would get 8 times 3/4 plus 9 times 1/4 to the S. So this is sort of like a weighted arithmetic versus a weighted geometric mean of the two. And this is 8.25, and this is about 8.24. So this one, so the expected value here is much bigger than the typical value. And so as a consequence, expected value of Z will be much bigger than expected value of, or much bigger than Z with probability tending to 1. So, and this is even when we've conditioned on the total number of edges, the expected number of independent sets is not concentrated. So, and it's because of the sort of just these very local fluctuations that some local neighborhoods are, better at having independent sets than others, even though they have the same number of vertices and edges. And you can have fluctuations in those. You can have, there's a binomial number, so you can, again, have rare events where you have more of these type 2 than you would normally expect. And that will give you and those sort of rare events will dominate the expected value. So sort of so if we wanted to calculate the sort of the right value of, or like the typical value of Z, we would somehow need to condition on not just the total number of edges, but also the fraction of local neighborhood types. And that's why sort of very sharp results for, say, the satisfiability of random constraint satisfaction problems have only been proved in sort of the Erdős-Renyi setting in in sort of one example, which is for k-sat when k is big. And that involved actually doing, actually conditioning on the number of local neighborhoods of depth r, and then letting r tend to infinity in the right way. So that's so the sort of fluctuations in the local structure of the graph in Erdős-Renyi random graphs causes a lot of problems. On the other hand, if we looked at random regular graphs, there are no fluctuations in sort of the local neighborhoods. Every local neighborhood looks like a regular tree, except the very occasional ones with cycles. So we should expect that in the random regular case, moments might behave better, and generally they do. So, but it's not as easy to write down the expected, let's say, the expected number of independent sets on a random regular graph. But there's sort of a recipe for how to do that, and so that's what I'm going to talk about next. But any questions about these examples? Yeah.
So you were saying that for the Erdős-Renyi graph, you need to truncate these like the rare graphs, like historical.
Yeah. So just like we found for colorings that it was better to first to fix the number of edges before taking the expectation. Actually, maybe it's good to sort of say, why was it enough to just fix the number of edges for colorings, but not enough in the case of independent sets? Okay. And the reason for this is that colorings are sort of more symmetric. So again, we can look at what happens when we add in one extra edge. So we have our graph, and we pick two vertices to connect up. In a coloring, you can ask, what's the marginal of these vertices? Well, just by symmetry, each vertex always has the uniform marginal. I mean, every vertex has probability 1 over k of being blue, say. But the joint distribution might not be independent for the ones we add in. But at least if they're vertices that are chosen a long way away, you can hope that they'll be at least close to independent of each other. So most of the time, you can hope that the change zgi plus 1 over zgi, this will be equal to 1 minus 1 over k. This is for colorings. For independent sets, on the other hand, in this vertex, what's its probability of being in an independent set? And this corresponds to the hardcore model with lambda equals 1, just the uniform distribution of independent sets. Well, there's 3 independent sets on this graph of size 2, either the empty one or you choose one of the 2. So this has probability a third. On this vertex, it's just isolated. There's 2 independent sets, either it's in or it's out. So this has probability a half. And then ZGI, and generally vertices with higher degrees will have a smaller probability of being in the independent set, because if I ask this one to, if you had a vertex with a very big degree, making this in the independent set means lots of other ones can't be in the independent set. Okay. So what's this ratio? Well, it's the probability in GI that sigma u equals sigma v equals 1. If they're chosen a long way away from each other and are hopefully independent of each other, we could at least hope that this is, 1 minus this. We could hope that this is like 1 minus probability sigma u equals 1, sigma v equals 1, both in GI. Okay, but these both depend on which vertices that we picked. And so in general, this ratio will be random. In the coloring case, we could hope that it's almost always equal to 1 minus 1 over k, or at least close to that. In the independent set, it will be some random variable. And okay, if I give you a product of, let's say un is a product of IID random variables, when is un approximately the same as its expected value? Well, it's only when wi's are deterministic. So products of random variables, when they're like really random, are never concentrated around their expectation. And this sort of adding in one edge at a time is sort of a lot like multiplying by a lot of kind of independent random variables. And so then if I think of ZGM, product of 1 to m of ZG I over ZG I minus 1. These are not IID, but they're still roughly independent of each other. And you just don't expect like products of random variables like this to be concentrated around their expectation unless they're just like constants. And in the coloring case, they are. And in the independent set case, they aren't. So this is why not all equal sat is easier to deal with than random k-sat, because in random k-sat, you add in some clauses, some variables start to become more likely to be true or more likely to be false. And then when you add in a new clause, the probability of it being satisfied will depend on which sort of ones you connected up. Whereas in not all equal sat, they remain all equally likely to be true or false. And the probability of your clause being satisfied should stay essentially the same. At least as long as this approximation that the marginals are of sort of faraway vertices, or that faraway vertices are basically independent of each other. Okay, so in the case of coloring, we can this works out nicely because of the symmetry of the colors means the marginals aren't dependent on the graph. For independent sets, the marginals do depend on the graph, and you don't get the concentration. Any questions about that? Okay. Okay. So how would you calculate the expected value in the partition in a random regular graph? Okay. So I'll do this on the configuration model. And so we'll have pairs, graphs, and configuration sigma, and I'll let H sigma of xy be the empirical distribution over pairs of neighboring vertices. So it's 1 over dn. And I'm thinking of this as like ordered edges of so I'm just looking at the fraction of vertices that are x on one side and y on the other. And I'm counting them as sort of ordered ones. But so h of xy will be equal to h of yx. Yeah.
Sorry, just a question. So when you talk about symmetry, you're talking specifically about like translation symmetry of like
I mean,
changing U and V to different.
no, I mean sort of like symmetry of the colors. So if you take a coloring of the graph, you know, if I have one coloring, I can permute all the colors and get another coloring. So each vertex has exactly 1 over k of being blue or red or each of the k colors. And that doesn't depend on the structure of the graph at all. So the marginals are always the same, regardless of what the graph is. And that's true for colorings, but not for the independent sets. Because in independent sets, the ones and the zeros, whether you're in the independent set or not in the independent set, is not symmetric with respect to each other. Okay. So this is the edge empirical distribution. And I can define the vertex empirical distribution as h bar of sigma of x as just being the same thing except with vertices. And because it's regular, I can just sort of sum over y of h of x, xy. So this is the fraction of vertices that have state sigma, or state x in the coloring sigma. And what we'd like to say is how many pairs G and sigma do we have with h of sigma equal to some particular value of h? So we want to count the number of ways of forming a pair of a graph and a configuration on the graph that give us a particular edge empirical distribution h. Okay, and we can compute this in sort of much the same way as we did with the configuration model. So if I wanted to, build a pair G and sigma with this particular edge empirical distribution, I could sort of do it systematically by starting off with the n vertices, and I'll grab some colors. So let's imagine we're doing a 3 coloring of the graph. So we'd want to pick n times h bar of 1 to be vertices to be in state 1, then n times h2 to be in state 2, and n times h bar of 3 to be in state 3. So first I'm just going to assign the colors to the vertices according to the vertex empirical distribution. And the number of ways of doing that will be n factorial over product over I equals 1 to the number of states we have, n choose h bar of x, or h bar of I, factorial. So it's just a multinomial formula. And if we do Stirling's formula, this will be e to the low of n plus h, the h times n, where this is the entropy function. So capital H of a vector, or a probability vector, will be sum of over I of minus xi log of xi. And so if you do Stirling's formula, you just get this approximation. Okay. So now I want to add in edges, but I'm going to, for each vertex, it will have d half edges coming out of it. And now I'm going to choose where they're going to be connected to. So, so I'll put a blue one here if it means that this one has to be connected to a blue vertex. This is blue, this is blue. These two are blue. And okay, and then I guess these two would have to be red. So this is telling us which of these half edges we're meant to connect them up to. So, so how many ways are there of doing this? Well, for each color X, we have d times n times h bar of x half edges to color. And we've got to divide them up according to h. So we need to split them into groups of h of x1, or dn times h of x1, dn times h of x2, and so on. So the number of ways will be dn h bar of x factorial. So another multinomial coefficient. H of xy factorial. And we do this for each of the x groups. And then if we did Stirling's formula again, we would get d times n h of h minus so we could think of this product of multinomials as sort of as a big multinomial with n factorial over all of these terms, and that would give us sort of the entropy of the vector edge empirical vector h. But then we'd have to sort of have in another term which would be divide. So, well, okay, let me write it out like this. You think of it as dn factorial over product of x and y of dn h of xy factorial times dn factorial over product over x dn h bar of x factorial to -1. So
Sorry, I was wondering what H bar was, but I already forgot.
okay, yeah. Yeah, so H is for the edges, H bar is for the vertices. Okay. So then what's left is we've got to make a graph out of this. And now we can take all of the edges where it's the vertex is green and it's going to be matched to a blue one, and take the corresponding blue vertices that are going to be matched with a green one. And then we take a uniform matching of these. So maybe this connects to this one, and this one connects to this one. And then we have red ones that are going to connect to blue with blue ones that are going to connect to red, and we match up those. And then the last ones are greens with reds. And then that forms a matching with a coloring, with an assignment of this. So that will give us a graph, or at least a multi-graph according to the configuration model. And it will be one with, and the coloring or the assignment of vertices that we chose is constructed to have exactly this edge empirical distribution H. And so now we should just count the number of matchings that there are. And I'm probably getting down to the lower bound of the board. Okay, and so the number of matchings is, so for each pair X and Y, then there's dn H of X, Y, and we're taking, this is a matching of just, we're connecting up green-blue vertices with blue-green ones. So it's just the number of those, X, Y, factorial. And then because I did 3 colorings, there's no vertices of type red that get matched to other ones, but in a general system we could have H of XX being positive. And so we get M of dn H of XX. Okay, and again, if we do Stirling's formula, we get MDN, just the total number of matchings of the that you can do, and then minus dn over 2 entropy of H. Okay, so if we multiply the number of ways of coloring the vertices, the number of ways of assigning the half edges, and then the number of ways of matching them up, so the total number of pairs G sigma with H sigma equals H, we will get X of so MDN e to the n d over 2 entropy of H minus d minus 1 entropy. and then plus a little O of n term there. Okay, so this is the total number. And then if I wanted the expected, so now take the expected value over a graph of the expected number of sigma, such that h of sigma equals h. Well, it will just be this divided by the total number of graphs, the total number of matchings. So x of h bar plus the lower bound. Okay, so in a random in a configuration model, this tells us the expected number of times we expect to see a particular edge empirical distribution when looking over all of the number of ways of coloring the vertices. Okay, and
Top products was have x not equal to y, or you also include
oh yeah, you're right. That should be x not equal to y. Okay, but now remember our formula for the weight of a configuration was product of psi of sigma u sigma v, product of over sigma v and e. Now, if I tell you how many edges have a particular pair, sigma u equals x, sigma v equals y, and I tell you how many vertices u have sigma u equals x, I can, just tell you what the value of this formula is. So the expected partition function will be sum over all empirical distributions, x of the lower of n plus h bar. And then you get so plus d over 2 h in a product with log psi plus h bar in a product with psi bar. And now we're summing over, this has a sum over possible edge empirical distributions here, but there's the number of these that you can have is only going to be each value of h, hxy, has to be like a multiple of 1 over n. So there's only n possibilities for each one. So this sum is something that's polynomial. So we'll be able to sort of absorb the sum into this little o of n factor here. And so the theorem is that if I write phi of h equals h of h, h bar log psi psi bar, then log 1 over n of expected value of z is equal to the maximum over h of psi of h plus the low of 1. So if I want the exponential growth rate of expected value of z, I just maximize this function, and well, that's it. So yeah.
Sorry, where's n on the right hand side?
On here?
I mean,
Oh, this.
you define phi n?
Sorry, that was an h. Yeah, so I picked the empirical distribution that will give us the best contribution, and it's just that. And because things are on the exponential scale, the sort of sum over h becomes a maximum over h. Okay, and so if we want to calculate expected values, all we have to do is some optimization, some sort of deterministic optimization problem now. The tricky thing is, so these parts are linear in h, but this is the difference between these h and, so these are entropies, so they're concave, but you have a difference between two concave functions. So you have to do a optimization over a function that's neither concave nor convex. And so in general, that can have more than one maxima, and indeed, indeed we'll see that that can be the case. And actually, don't know how I'm going for time. Well, the next theorem, which I think maybe I will defer to tomorrow, will sort of give a characterization of what h has maximized this. So so if we have some h star such that phi of h star is the maximum of phi of h, so a maximizer, then there exists an m such that, okay, m is a fixed point of the BP equations. And h of xy is equal to some normalizing constant times m of x psi of xy m of y. So, or another place you'll see this equation is, okay, so what does this say? Well, m is a fixed point of the BP equation, so this corresponds to a translation invariant Gibbs measure on the infinite deregular tree. And then if you look at two vertices, two neighboring vertices, say u and v, and look at their joint distribution, well, you take the messages m coming in both directions and then compute the joint distribution of these two. It's exactly this formula. So what it's saying is that the maximizers correspond to finding fixed points of the, or finding these translation invariant Gibbs measures, which you can do by solving the BP equations, and then the empirical distribution that you see will be given by the empirical distribution of that Gibbs measure. Okay. Any questions about? Yeah.
So do you know how quick, so going back to your previous theorem, sorry, do you know how quickly it goes to 0? Because this is for a fixed n, but log n, right?
How quickly? Yeah.
It's a little O of 1 here. Do you have an idea of how quickly it goes to 0?
Yeah. So I'm being. Oh, yeah.
Yeah.
So actually, quite quickly, and actually, what we'll see is if the BP equations behave sort of nicely in a neighborhood of the fixed point, then what we'll get is actually that expected value of z over e to the n phi of h star, the maximizer, that this will converge in distribution, so to some random variable w. So you know, in this, the way I've written things here, the fluctuations could be as big as, like, you know, e to the square root n, or e to the n to the 1 minus epsilon or something for z. But actually, why am I? So sorry, this should converge to a constant. But actually, if I get, well, with some, yeah, if the second moment method worked, this without the expectation would converge in distribution. So this is, so there's no extra, there's no real extra term here. Now in the proof I gave, where did the little o of n factors come from? They were all really like the square root n's you get in Stirling's formula. And so in principle, we should have some sort of polynomial correction. But then there's also the part where we sum over all the possible values of h. And there's polynomially many of those, and they cancel out. So actually the convergence should be quite good, and should be sort of like the rate of convergence should be related to the rate of convergence to like Stirling's formula. So you shouldn't expect it to be. I mean, in principle, this we could be off by quite a bit here, but in general, we won't be. Yeah.
So this is the configuration model, right?
Yes.
We start with the random regular in mind. So do we get for free the result for random regular via the fact that if something goes with high probability?
That's a great question, and so there are some. I mean, it depends a bit on the model that we're looking at. So if we can think of the random regular one as conditioning, as taking the configuration model and conditioning on there being no self-loops or multiple edges. Self-loops, for instance, could make a sort of non-trivial difference if we were talking about, say, colorings of the graph. If you have an edge that connects a vertex to itself, then you will get no colorings. On the other hand, at least, like, if we were in the permissive case where there's always a way of assigning. Yeah. Okay. So let's suppose that all of our psi xy's were greater than 0. So not colorings or independent sets. then we would have that in the configuration model. So, okay. No, actually, we're going to need a bit more to be able to make that kind of comparison. And yeah, so if actually, I forgot that we stopped at 20 past and not half past, so I should, but I think we started 5 minutes late, so this is, I think I've got my full hour and a half. Okay, but to quickly answer your question, if we can do the second moment as well, and we'll be able to write the second moment as like a spin system where we have 2 values on each vertex. So you could also do an optimization problem like this. If you can do that, then Z will be concentrated around its expected value, and you'll have that both in the configuration model and in the random regular one, as long as say you have some, you have non-zero values for psi, and if you have 0 values, then you have to be a bit more careful, but it should still usually be the case. Okay, so let's finish off there and go to lunch.